Oh, there you go, Kyle. It says I got 6 people watching right now. Who else is here? I'm not actually getting started yet. I'll get started around 1:10ish. Cal, you can't time people out unless they comment. Otherwise, they're unknown to the masses. It's funny. In the description, there is a link to a PDF file of the questions that I'm going to be reviewing today. I'm going to number the questions according to that PDF file. So if you need some kind of reference, you can look at that and look at the video and just see what it is that we're actually going over. Hopefully, you all got my update on the AP test and how they're going to be handling it. It's mainly going to come down to 2 free response questions that are probably going to be a bit more difficult than what they typically are. You will not have any chi-squared on the AP test, and seemingly you will not have any. Well, you could have regular linear regression stuff, but you won't have anything in regards to hypothesis testing linear regression. So that's where we're at. I gotta make one more check real quick. I gotta close out some things to make sure my window's gonna be working properly. I don't know if you all saw on Twitter. It's my son's birthday. Typically on his birthday, I would be working anyway. So this is nothing new. Oh, and there's a knock at my door. Just on time.
Could you help me open this?
Yes, I can. Come in for a second. And then you're going to work on this on your own?
Yeah.
Okay.
No directions. friends.
I hope so too. So, for those who can hear me right now, my son has joined me. He got, well, I'll flash it across the screen for a moment. He got this as one of his birthday presents from his grandmother, and he's super excited. I'm just trying to open up the box so he can put it together. Oh, there it is. You see there's a little perforated edge here?
What is it
Oh,
supposed to
supposed to, like that. There we go. I know, it's a little tricky.
I was trying to do that.
So let's see what we got in here. These look like the directions, maybe? Yeah. These look like the directions. They look like a lot of directions.
Yep.
You gonna be okay?
Yeah.
Okay. If you have any trouble, ask Mom when she gets out.
You can get an Iron Man one.
I know, and I'll check in with you later, okay? All right. There we go. Okay. I would like to get started. I remember I was just reading Kyle's comment. Nice. Actually, today my son has gotten a few Lego sets. We got him an X-Wing from Star Wars, and he pretty much put, well, a little help from my wife, put the entire thing together himself. He was very, very proud of himself. I mean, who wouldn't be? He saw Star Wars for the first time. It was awesome. It was fantastic. Anyway, let's get started. So like I said, in the description and in the chat, I typed in a link to the shareable Google Drive PDF that you could use in order to get these problems done. I'm going to be going through them one at a time. Basically, the nuts and bolts of this is hypothesis test review. Based on the question, based on the information that they give you, what is it that you have to do? What test do you have to perform? If you have any questions while we're going through this, please, by all means, make sure that you type them into the chat as we're going along, and we'll kind of see how this goes. So I'm just going to start very simply with number one. Again, the PDF is in the description. Number one, a random sample of 49 medical doctors. I'm going to stop and do one of those, okay? Random sample of 49 medical doctors in LA showed that they worked an average of 53.1 hours per week, okay? With a standard deviation of 7.2 hours per week. If the California average is 60 hours a week, now, based on that statement, if the California average is 60 hours per week, we're dealing with a population parameter. They are assuming that it is 60 hours per week. So I'm going to put mu is equal to 60. And then the question then becomes, does this give evidence that the LA doctors work significantly less than the rest of California? Excuse me for one moment. There is knocking at my door again. James, I'm in the middle of a lesson. Despite all of my warnings, my son still knocking at my door. Anyway, I'll get to him in a little bit. So the question then becomes, as I said, does this give evidence that the LA doctors work significantly less? The California average is 60 hours a week. This random sample produced 53.1 hours per week with this standard deviation. Is this evidence that Los Angeles doctors work less? So, first, let's just kind of talk about what kind of test we need for this particular thing. We don't have the population standard deviation. We don't. So since we don't have the population standard deviation, no sigma, we have quantitative data. I'm not going to do this for every question. I'm just kind of going through a logical progression. We don't have a population standard deviation. We have quantitative data. According to that, we need to run some kind of t-test. This is kind of the logic that I want you guys to go through. Several lessons back, I don't even know how many times I did this, probably 2 or 3 times, I wrote a flowchart for the type of tests that you should run depending on the information that they give you. We have quantitative data and we don't have sigma. We have to do a t-test. That could be a 1-sample t-test, a 2-sample t-test, or a matched paired t-test. We'll see all of those today at some point. This is obviously a 1-sample t-test that we want to run. Now this is just preliminary information. Now I actually have to go through the hypothesis test. So the null hypothesis is the California average. Based on the question being, does this give evidence that LA doctors work less than the rest of California? So the alternative is that mu is less than 60 hours per week. This is, again, for a hypothesis test, we walk through 4 steps. The hypotheses, the assumptions and conditions, actually performing the test, and then a conclusion. This is the hypothesis. We're good with these. Now, we have to go through assumptions and conditions. Now, since we're doing a t-test, we don't have to have a large enough sample. We don't. We do have to make sure about normality, which there's a little bit of a hiccup with this problem. We'll deal with that in a little bit, but let's go through the rest of them. First of all, assumptions, conditions. Random sample stated. It said in the problem itself a random sample of 49 medical doctors. Now, independence is also a big deal. Now, since it is a random sample, and I can justify this by it being a random sample, I can say independence of hours worked because of random. The sample size is 49. 49 is less than 10% of California doctor population. Oh, Joe is promoting Club Penguin all of a sudden. Oh, Joe. Anyway, back to this. Now, to do a t-test, the 4 main bullet points, randomness, independence, less than 10% of the population, the last one being nearly normal. If you go back to the problem itself, it does not say anything about it being normal. It just says a random sample. It doesn't give you any information in terms of the data that was collected, like the individual data points, all 49 data points or something like that. We don't know anything about normality. Now, this is a little bit of a hiccup, but we still have to make a statement, make some kind of address to the nearly normal condition. Now, what I wrote in my little notes here, I did nearly normal, question mark. Now I'm going to write something else in a moment, because again, they don't say anything, but I have to address this condition. Ask yourself the question, and this is a rhetorical question, ask yourself the question, is there any evidence to suggest that it's not normal? We're looking at all doctors in California, number of hours worked per week. Some may work a lot more, some may work a lot less, but on average, it's reasonable. So you could say something to the effect of reasonable to assume hours worked is normal. It's reasonable. They don't mention it. They don't say anything about it. They don't give you any data to kind of confirm or deny this. Typically, we have to look at a histogram, but they don't give us anything. You still have to address it. Reasonable to assume normal. Let's perform the test. Now, I'm going to show you 2 ways to perform this test. One using the graphing calculator test itself, and one using TCDF. Now, if you were going to use TCDF, first you got to get a t-score, and I'll explain why in a moment. If you're going to do a t-score, we got the sample minus the average divided by the standard error. Sample standard deviation over the square root of the sample size. It's the typical way that we've been doing this since, I don't even know what, chapter 17 or something like that. If you did this calculation correctly, it should give you something like negative 6.71. Now, z-scores and t-scores obviously are related, but you can't assume that they are exactly the same thing. This is a t-score. A t-score of negative 6 and change is not exactly the same as a z-score with negative 6 and change, which again, we'll deal with that in a minute. If you were going to do t CDF, not the same as normal CDF. Lower limit, upper limit, but the t-CDF in the graphing calculator, and I'll show you this in a minute, the t-CDF in the graphing calculator does lower limit, upper limit, degrees of freedom. That's what it does. Lower limit, upper limit, degrees of freedom. Now, I'm going to go small number, comma, negative 6.71. Because if you were thinking something that's nearly normal but not exactly normal, we're looking at a t-score of negative 6 and change or less. We're going less than. Degrees of freedom, 48. Degrees of freedom for t-test, obviously, we're going to be going n minus 1. Let me get my graphing calculator going. Just kind of show you what this thing looks like. Let me reset. I have a whole bunch of stuff in here. I was doing practice before. Let me calculate the exact value of the t-score. There it is. Negative 6.708, blah, 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 blah. I'm going to be going t-CDF, small number, comma, that answer, comma, degrees of freedom, which in this case are 48. This is our p-value. The p-value is to be interpreted exactly the same as we always have. 1.03 times 10 to the negative 8th power. This number is approximately 0. It's approximately 0. It's way small. Yes, we are going to reject the null hypothesis. We absolutely are going to reject the null hypothesis. Now, if you were not going to do t-CDF, let's say you wanted to use t-test. I don't have data. I'm going to put the stats in. My mu would be 60. My sample mean would be 53.1. My sample standard deviation would be 7.2. And my sample size would be 49. The alternate hypothesis, we got to go less than. All calculated out correctly. You can see it gives you the exact t-score that we calculated by hand, and it gives us the exact p-value that we just calculated before. Those are the numbers that you would need. Step 1, hypothesis. Step 2, assumptions, conditions. Step 3, perform the actual test. Step 4, proper conclusion. With a p-value so low, approximately 0, we reject the null. Again, always make a statement of rejecting or failing to reject, something along those lines, but then you got to put it into context. Oh, look, there's Jacob. There is evidence to suggest LA doctors work less hours than all Cali doctors. Jacob, you better wake up that notification crew. I don't know where any of them are. That notification crew never gets my notifications, apparently. They need to be notified. Wake them all up. Also, Jacob, just in case you're wondering, the problems that I'm working on, there is a link in the description to the PDF. In fact, I'm going to paste that link one more time into the chat. There it is. But yeah, this is what we have for this problem. Now, again, the goal for today, which hypothesis test do we use? And once we determine which hypothesis test we use, well, we have to actually perform the proper test. And I have so many pieces of information to give you. Yes, that PDF link is to all the problems that I'm working on. This is obviously number one. Now, I'm not going to be going over all of them because on that PDF, there are some chi-squared problems. And because of the recent announcement by College Board, we are not going to be doing chi-squared on the AP test. Thankfully. That would be a bit difficult to learn on your own without me. But, I mean, it's possible, of course. All right. Let's talk about number 2. Now, again, with getting number 2 ready, PDF in the description. Let's go through it a piece at a time. Now, as I'm reading it, of course, I am going to write down the important information that we need. Just as a side note, whenever you see those words, test statistic, as you saw in number 1, it says like requirements and then test statistic, blah, blah, blah. The test statistic is your t-score. Or if you were doing a z-test, it would be your z-score. Yes, Jacob, this is a different chi. The chi that I'm referring to is a Greek letter, C-H-I. But I digress. Let's go to number 2. Usually, white blood cell counts are normally distributed. Now, they automatically say it, normally distributed. This is very helpful. The fact that they tell you that they're normally distributed. We'll deal with that later. Cool. But they're usually normally distributed with a mean of 7,500. Okay? Looks like a population parameter to me. If a patient has taken 50 laboratory blood tests, wow, I don't know why they would take that many. But they took 50. That's the sample size. That have a mean of 72, 13, 75. Wow, that's weird. That's a sample mean 72, 13, 75. Looks like their white blood cell count is smaller than what they assume that population mean is, with a standard deviation of 393.44. Okay. Does this give evidence that his white blood cell count is significantly different than normal? Okay. Let's go through this a piece at a time. Now, they did say it was normally distributed, which is nice, the fact that they gave you that. But I'm still going to go through a few assumptions conditions. The reason why is because we need that normal assumption for the nearly normal part. We'll deal with that in a moment. Let's figure out what test we're going to use. We don't have sigma. We're still dealing with quantitative data. We will eventually use a one-sample t-test. If you're dealing with quantitative data, that it makes sense to take an average of, a mean of. Whether you use a t or a z is solely depends on whether or not you have sigma or you don't have sigma. We don't have sigma, we're going to have to do a t-test here. So, assumptions, conditions. Well, actually, no, I don't want to do assumptions, conditions yet. I want to do my hypotheses. That's what I really should be working on first. Now, they assume mu is equal to 7,500. The alternate. Now, I'm going to reread that last statement. Does this give evidence that the white blood cell count is significantly different than normal? Immediately, by me rereading that, you're automatically like, Oh, it's got to be not equal to. And you're right. Mu is not equal to 7,500. Now, yes, his sample is significantly, well, not significantly, it's just less than the 7,500. But with the null and alternate hypotheses, these are the ways that you're going to have to write them out. Assumptions, conditions. They do say the patient has taken 50 laboratory blood tests. Wow. That's weird. Why would he take 50 blood tests? They say nothing about being random. Is it reasonable to assume that each blood test is random? I don't know, it's taken from the same person. The question that they're really asking is, does this give evidence that his white blood cell count is significantly different than normal? Not other people's, but his. You could say, well, randomness, reasonable if blood tests not all taken at same time. Like, if this guy took 50 blood tests over the course of like a year, then I'd say, okay, we're good. We're totally fine. But if he took them all like over the course of a weekend, that's a bit sketchy. Again, they don't really speak to that. If you wanted to speak to that, you totally could. The context of the situation means everything. You could say independence of blood cell or white blood cell count as long as randomness is reasonable. The only way that you're going to get independence in this case is if randomness is reasonable. Independence relies on that randomness. And again, that's a bit sketchy, but we'll deal with that. 50 is less than 10% of all possible blood tests that can be taken. Again, realize that this is all one guy taking 50 blood tests. Don't know why. Thankfully, normality stated. They said that typically white blood cell counts are normally distributed. It is reasonable for us to then take that and be like, yay, normality stated. We're doing a one sample t-test. But keep in mind that because it's not equal to, we're going to be doing two-sided. Like, for example, it may end up being something like this. It's going to be two-sided. So whatever p-value we get, we're going to have to double in the end. Yes, Kyle, but my rationale is, like, if you take a blood test at 1:30 in the afternoon and then take another blood test at 2:30 in the afternoon, they're not going to be that different, or they shouldn't be reasonably. Anyway, back to this. Oh my gosh, I don't even know what I'm doing. Those are my notes. I should keep them down here. So let's actually calculate this test statistic. Well, Kyle, what do you mean 49 is too low? Shut up, Kyle. Anyway, ruining me. Let's calculate this. 7213.75 minus 7,500 divided by 393.44 over the square root of 50. If you were to do this, you would get a t-score of approximately negative 5.145. Again, this is your t-score. It's low. Seemingly, we're going to get a low p-value once we run this thing. let me kind of do through the calculation. I'm going to show you the calculation on paper, and then I'm going to show you the t-test calculation on the calculator. You would do something like TCDF, parentheses. Well, no. Yeah, I would go small number, comma, negative 5.145, comma, 49. Again, that negative number would put us over here. We'd have to go small number up to that t-score. But ultimately, we're going to have to double this. We're going to have to double it. This, we do this on the calculator here. There we go. 7213.75 minus 7500 divided by 393.44 divided by the square root of 50. I'm going to have to here we go. Put an extra parentheses there. Japow. There is our t-score. TCDF, small number, comma, that answer, comma, degrees of freedom, America, gives us approximately 2.35 times 10 to the negative 6. But again, because it's two-sided, because we're doing not equal to, we have to double it. We have to double it. So the real p-value, 4.7 times 10 to the negative 6. That is the real p-value to this problem, and that's the p-value that we're going to base our conclusion on. Let me show you what it would look like in the calculator with the t-test. If you're going to do a t-test here, your mu, 7,500, x bar, standard deviation, sample size, not equal to, calculate. You can see their p-value is the exact same as my p-value. Same t-score. Always double check that t-score. It's always good to have that information. P-value is way too low. We reject. Because p-value is approximately 0, we reject the null. There is evidence to suggest, or it appears, or whatever floats your boat in terms of fluffy language. There's evidence to suggest this man's white blood cell count is lower than 7,500. There is statistically significant evidence. One might say statistically speaking, although I cringe at that phrase. Talking to you, Santino, wherever you are. Anyway, let's talk about number 3. Now I'm looking at number 3. Number 3 is a different beast. Number 3 is not going to be exactly the same. Yeah, he's probably MIA. Did you know that I made that assignment to respond to me in regards to people's status of taking the AP test, and all but 2 of you got back to me. All but 2 of you. Made me sad. I'm not going to tell you who they are. Not going to tell you who they are. But Santino did get back to me. That's the point of me saying that. Anyway, back to this. Let's talk about number 3. Number 3. USA Today reported in 1992, 39% of all elementary school children claimed that when they grow up, they want to do something to help other people. However, in 1995, now hold on, let's back up. In 92, 39%. That 39%, now you're going to figure it out based on what the entire problem looks like, but that 39% is actually a population parameter. However, in 1995, 128 in a random sample of 317 of these same children claimed that when they grow up, they want to do something to help other people. Does this information indicate that there has been an attitude change either way? The 1992 39% statistic is a population parameter. They don't give you any other information. They don't give you the sample size. They don't give you anything. But then in 1995, there's a random sample taken, and they want to know, have attitudes changed either way? It's the same children, yes, I understand. This is all the information they give us. And this is what we have to work with. Yes, Jacob, you were one that responded. So good for you. Now, based on the fact that we are given proportions, we automatically are going to be using a z-test. Based on the fact that they gave us proportions, we are automatically going to be doing a z-test. In fact, this is going to be a one sample z proportion test. Why is that not focused? A little better. Yeah, it is going to be a one sample z proportion test. That 39% from 1992 you have to assume is the population parameter. They don't give you any other information, but this is what we have to work with. Let's talk about a null and an alternate hypothesis. Null hypothesis. P is equal to 0.39. Alternate hypothesis. P is not equal to 0.39. Look at the question. The question in number 3. And again, if you're just showing up now, here is the link to the PDF. I'm going to keep doing that periodically. I'm on number 3. The question being asked, does this information indicate that there has been an attitude change either way? Now, if you were to actually do that calculation for 128 divided by 317, yeah, you get 48% and change. Obviously greater than. But because of the wording of the question, you have to do not equal to. You have to. Let's talk assumptions, conditions. Now we're dealing with proportions, so the assumptions, conditions are a little bit different. First of all, random sample stated. Random sample. Student responses independent of each other. That's reasonable, based on the fact that it's a random sample. 317 is large enough sample. 317 is definitely a large enough sample. Now they're saying 39% of all elementary school students. 317 is less than 10% of all LM students. But remember, again, all of your assumptions and conditions. You have to check expected successes and expected failures. And since we are assuming a population parameter, because we're assuming a population parameter, this is the calculation that you would have to do for expected successes and failures. Boom. 123.63, 193.37, both greater than 10. Expected successes, expected failures. Good. Because of this, boom, boom, boom. One sample Z prop. We can do that. We can absolutely do that. Now, again, I'm going to do the same thing I did before. I'm going to show you how you could calculate this by hand. And then I'm going to go through showing you how to do it on the calculator. Joe, are you threatening me, or is there a bee on my head? I don't know what Joe's doing. Somebody help. Okay, back to this. Now, if I was actually going to perform this one prob z test, and again, I'm checking the I did these problems ahead of time. Want to make sure I did the right thing here. Yes. Because it's not equal to, we're going to have to double whatever we get from normal CDF. And yes, we can do a normal CDF in a little bit. We could calculate a z-score at the moment. Let me just show you how you can do it like this. Normal CDF parentheses. Now I'm going to run out of room, so I'm going to have to elaborate on the next line. But with normal CDF, you're doing normal because it's a z-test. But with normal CDF, you're going to do lower limit, upper limit, mean, standard deviation. Now with this, lower limit. Because 128 over 317, because this number was approximately 40% and change. What was it exactly? 128 divided by 317. Yeah, 404. There we go. Because that number is greater than the 39%, we're going to go 128 over 317, comma, big number, comma, the assumed mean, comma, the standard deviation, which if you remember, 0.39, 0.61, which is the assumed P and Q, over the sample size. Close that giant parenthesis. There we go. Let's see it on the calculator. Normal CDF, 128 over 317, comma, big number, comma, 0.39, comma, the square root, 0.39 times 0.61 divided by 317. Boom! There's a p-value. No, actually, no, I apologize. That's not the full p-value. That would be the p-value if this was greater than. But it's not. It's not equal to. And because of that, we have to double it. The p-value of this particular problem is 0.6148. That's the actual p-value of this problem, which is way too large. And because that p-value is way too large, you are going to fail to reject, which we will do in a little bit. Let me show you what it looks like under tests. If you were going to do this, it would be a one-prop z-test. The assumed population parameter, x, and n, the sample size. It's already set to not equal to. Yes, Maddie, I will answer your question in a moment. Let me get this done. If we do this, you can see our p-value at 0.6148, which is the exact p-value that I needed. Maddie, you asked the question, can you explain how you decide it's a z-test? Absolutely, yes. Let me take a little bit of a rabbit trail. I'm going to come back to this page in one moment. I'm making a big deal out of this simply because I want to. Here we go. In terms of the type of test that you use, don't worry about one sample, two sample, matched paired sample. Don't worry about that just yet. We'll worry about that later. Right now, you need to decide whether or not you're going to do a T or a Z. That's the first main thing you have to decide. So the question is, what type of data do you have? What type of data do you have? Do you have quantitative data? Or do you have categorical data? Categorical is also known as qualitative. Quantitative data is when you're dealing with means. Categorical data is if you're dealing with proportions, which is what this problem was dealing with. If you're dealing with means, well, the next question comes down to whether or not you have sigma or you don't have sigma. That's a weird sigma. I'm going to draw that again. That's better. For problems numbers 1 and 2, we did not have sigma. And since we did not have sigma, we had to do a t-test. If you have sigma, which is rare, but they have to give it to you in the problem, I guess, then you would do a z-test. Now, Going to the calculator, if you look at z-test, t-test right here, under z-test, they have an option for sigma. Under t-test, they don't have an option for sigma. That's what it comes down to. Do you have sigma or do you not have sigma? The population standard deviation. Now, when you have proportions, categorical data, it's a z-test all the way. It is a z-test all the way. If you look at the test section of your calculator, proportion z-tests are separate from the regular z-tests. So if you have proportions, you have to make sure that you pick one that says prop. And then we go from there. Joe, just for the sake of argument, it's not sigma. It's, can I type this in? I'm trying to type this in. Sigma. Boom, there we go. I just wanted to make sure I clarified that sigma. Now, going back to our problem. Again, we were dealing with proportions. So automatically, we need a z-test. There's only one sample. It's a one-sample z-test. First, you need to decide, is it a z or is it a t? And then we'll deal about the rest of it then. How do you get sigma when he says sigma? What? Okay, I'm going back to my problem. Anyway. Yeah, I think I showed you, the last thing I showed you before I answered that question was for the one prop z-test, typing in all that information, and we got that p-value. That p-value is way, way too high. And because of that, because p-value is greater than 0.05, much greater than 0.05, we fail to reject the null. Always make that declarative statement. Either you reject or you fail to reject. We're failing to reject this time. You only reject if the p-value is lower than your alpha level. We fail to reject the null hypothesis. There is not enough evidence to suggest. Now again, I'm going back to the problem because I want to make sure I write it the same way the question was asked. Does this information indicate that there has been an attitude change either way? There is not enough evidence to suggest there has been an attitude change. Well, let me go back to that problem one more time. What were they asking them? They claimed that when they grow up, they want to do something to help other people. Okay. There has not been an attitude change in children wanting to help others when they grow up. It's always good to kind of throw the context of the problem into your conclusion. But this is a typical conclusion that you could give. Always make that declarative statement, either rejecting or failing to reject, and then put it into context. Use the fluffy language. Now, Maddie, you asked the question about how do you decide if it's a z-test, and I went through that whole chart. Number 4 is really going to make, hopefully, a little bit more sense in regards to what test do we use and why do we use it. Now, again, just as a reminder, I just want to remind people, in the description is a link to the PDF that we've been working on. If I'm talking about number 4, I am talking about that particular problem. So please make sure. Why is it so hazy? There it goes. It just fixed itself. Number 4. The manager of a sporting goods store offered a bonus commission to his salespeople when they sold more goods. A new manager decided to drop the bonus system. For a random sample of 6 employees, the weekly sales in dollars are shown in the following table for each employee, with and without the bonus system. The sample size is 6. Even though, yes, there's 12 pieces of data in that table. The sample size is 6. In fact, while I'm looking at the problem, let me enter in some information into a list. I need to get some more information. 2,900, 3,000, 5,800, 4,400, 5,300, 5,600, 2,800, 2,500, 5,900, 3,500, 4,600, 4,600. Okay. 1 var stat of L1. 1 var stat of L1. Let me just write down this information. X bar of 1 is 4,500. This might be helpful. It might not be helpful. We'll see what it does in a little bit. I'm just writing it down for my own sake because I just want to see what it looks like. 1 var stat of L2. Okay. Now, again, I haven't even finished reading the question. I'm just writing down the information that I think may be helpful later on down the line. Just see what happens. Let me just reread a little bit. So the manager of a sporting goods store offered a bonus. The new manager dropped the bonus system. Then they took a random sample of weekly sales of 6 employees. First with the bonus and then without the bonus. And that's in the table in the PDF. Here's the question. Does this imply that sales dropped when the bonus system was discontinued? First, we have quantitative data. Second, we don't have sigma. We don't. So, because of that, we are going to have to do some kind of a t-test. Now, here's the big question. Is this a 2-sample t-test? Or is this a matched paired t-test? Yes, there are technically 2 samples going on. With the bonus, without the bonus. There are 2 samples going on here. So which one is it? This is going to be a matched paired t-test. Matched pairs. And what that comes down to is the fact that the first sample and the second sample are not independent of each other. 2 samples, not independent of each other. They're not. Because it's the same employee. The sales both with the bonus and without the bonus, well, their results are going to depend on the employee. They're dependent on each other. Because of that, we have to do matched pairs. Now, it's actually going to be fairly simple in the calculator, and we'll deal with that in a little bit. But first, let's just see what we have to do here. What we really have to look at, there we go, oh, there it is the differences between with the bonus, without the bonus. You notice what I'm typing in there, L1 minus L2? There are my differences. L1 was with the bonus. L2 was without the bonus. You can see most of the employees, well, their sales actually were better with the bonus. And they're worse without the bonus. Most of them. One of them actually did go up without the bonus. I don't know. Let's see where this takes us. Let's just see where this takes us. For the sake of argument, a little note for myself here. There we go. Just a little note for myself. I'm going to do the average of the differences. And you would do an average of the differences if you were doing matched pairs. And it's going to be the mu of the bonus minus the mu of the not of the bonus. Or not having the bonus. Null hypothesis. The null hypothesis is nothing's going on, there's no difference, there's nothing happening, there's no change. The differences are approximately 0. Whereas the alternate hypothesis, the mu with the difference, well, again, let's go to the question one more time. If I go to that question one more time, does this imply that sales dropped when the bonus system was discontinued? That is the question that they are asking. They want to know, did sales drop? Is this number smaller now? As a result, we need it to be greater than 0 for the alternative. We need it to be greater than 0. Assumptions, conditions. Random sample stated. It's a random sample of 6. I can say that 6 is less than 10% of some population. I don't know what population. Let's just say like the employee population. People working at this store, the sporting goods store. I don't know how many people work there. I don't know how big it is. Just 6 people. Now, independence. We can't say that the samples are independent of each other, but what we can say is that the differences, or the difference in sales, are independent of each other. Each employee, their difference in sales is independent from each other. Now, nearly normal, you're going to have to look at the histogram of the differences. You're going to have to look at the histogram of the differences. Now, I looked at this one earlier. This one does not look that great. L3. Notice I put an L3 here. Zoom 9 it. There it is. It's terrible. That looks terrible. That looks horrendous. I don't know. Again, that's the beauty of statistics. The beauty of statistics is that, well, it looks close enough. Nearly normal. That's what the thing looks like. Unfortunately, that's what we have to deal with. So, let's take a look at what this thing does. First of all, the t-score, let's just calculate it by hand first. Oh, my daughter's awake. Great. First, let's look at the differences right here. Oh. Let me run a 1var stats on L3. There it is. X bar of the differences is 516.67 with a standard deviation of 440.08. I guess that rounds to. I just did a 1var stat of L3. If I was going to find the test statistic, it would be something like 516.67 minus 0, because that's the assumed difference, over 440.08 over the square root of 6. Let's just do that like that. These numbers. All right, fine. Let's just do it like this. Because obviously the top would just be 516. 516.666667, whatever, divided by parentheses 440.0757511, divided by the square root of 6. Boom. There is my approximate t-score. And again, I'd show you that on the calculator with a t-test in a moment. I'm just doing it by hand just to show you what it looks like. If you were going to do a t-CDF, it would be that number, big number, degrees of freedom. America. Again, the sample size is 6, degrees of freedom is 5. t-CDF, that number or bigger, 5, boom, kicks out a t-score of 0.0174. That p-value is small enough, we can reject the null hypothesis. I know that this seems very monotonous because we're doing the same thing over and over and over again with these problems, but it's important that you understand why certain problems are going the way that they are, why certain problems are doing t-test or z-test or matched paired or two sample. You'll see. Oh, you'll see. Anyway, p-value is less than 0.05. We reject the null. There is evidence to suggest. Now again, going back to the original question, does this imply that sales dropped when the bonus system was discontinued? Well, the null hypothesis was that they didn't drop. Innocent until proven guilty. We have evidence to suggest otherwise. There's evidence to suggest sales did drop after the bonus system was discontinued. There we go. Let's see. Yes. I'm going to go over two more questions with you guys. I'm going to go over numbers 5 and 6 with you guys. I don't want to take up all day, or all of your time, I should say, especially considering today is my son's birthday, as I've mentioned. But obviously, I'll do a little wrap-up at the end in regards to which problems you should and should not try after the fact. But let's talk about number 5. Number 5. In 1975, a random sample of 1484 adult U.S. citizens was surveyed, and 193 strongly agreed with the statement, people should take care of themselves. Random sample. X bar of 75 was 193 over 1484. Okay? And then another sample was taken in 1991, in which 61 out of 1013 strongly agreed with the statement. Now, just for the sake of argument, 193 over 1484 is approximately 13%. And the other one is approximately 6%. Now, this is an amazing question. They're all amazing, but I think this one's the best. Does this indicate that the proportion of U.S. adults who strongly agree with the statement has dropped? This is a two-sample z-test. This is a two-sample proportion z-test. Obviously, you're dealing with proportions, but you're dealing with two independent samples that get you a proportion. You're dealing with the z-test. We're going to have to do normality. We're going to have to do all that stuff. Actually, yeah, we'll do normality. We don't have to do nearly normal, though. Nearly normal has to do with t-testing. For z-testing, we just have to do randomness, independence, large enough, less than 10% of the population, and expected failures and successes, which we'll deal with. We will deal with all of that. Let's deal with a null hypothesis. Null hypothesis, there is no difference between the two. Well, if I'm going to write out this null hypothesis, the population parameters difference would be 0. But now they're saying, did it drop? Is this number smaller? Has it dropped? Which means the alternative is greater than 0. Meaning that, the alternative being that the 1975 proportion is larger than the 1991 proportion. Has 1991 dropped? That's what we got. So, where do we go from here? Random sample stated. In fact, for 1975, they said a random sample was stated, but then in 1991, it was a survey. Again, yes, the survey, you can assume that it was a random sample. You could say that 1484 and 1013 are less than 10% of U.S. population, because they just surveyed U.S. citizens. You could say that 1484 and 1013 are large enough samples. Now, I wrote down these numbers, but of course there is no expected success and failures. So unfortunately, you have to do with the given expected and failures. 193 and 1291 and 61 and 952 are greater than 10 successes and failures. Just did it all in one shot. The 193 and the 1291, the 61 and the 952, I just did it all in one shot. Greater than 10 successes, 10 failures. And independence. Now, the independence, you could say that the samples are independent of each other. You could also say that citizen responses are independent of each other. Two sample proportion z-test. There we go. Now again, I'm going to show you how to do it by hand, and then I'm going to show you how to do it using the test in the calculator. But keep in mind one major thing. Because of null, we pool the p-hat. Because of the null hypothesis, we pool the p-hat. Because the null hypothesis is assuming there is no difference between the two, we're going to have to pool the p-hat in regards to the the standard error. You'll see that in a little bit. It's going to be great. For me, mainly for me. If you're going to calculate a z-score, this would be the 13% minus the 6% minus the anticipated average over the standard error. The way that the standard error would have to work. Well, first, let me pool the results. If I am pooling the results, yeah, 0.102. There we go. I'm rounding a lot of these results. That would be the pooled 0.102. That would be the pooled p-hat. And if I am going to be doing the standard error, it would have to be the square root of the following. I'm writing this out, and then I'll explain what's happening with this. Yeah, I ran out of room there. There we go. It's very odd to see. I'm going to show you what the calculator does in a minute. And I'm going to program some stuff into my calculator. It's going to be amazing. But with the standard error, typically with two samples, you have to square the standard deviation, add them together, square root them back. That's typically how we find standard deviations. With this problem, we are assuming there is no difference between the two. And because of that null hypothesis, we have to pool the p-hat, which is unfortunate. But you can see the p-hat, q-hat, the p-hat, q-hat, a little hazy there, over the different sample sizes. It's a very strange process. If this were a two-sample proportion interval, then we would not pool them. We would not pool them because we don't know what the population parameter is. We're not assuming a population parameter. We're trying to find the population parameter. But for a test, you have to assume it. It's very strange, very odd. Again, if you were doing this whole calculation, let me just show you what this would look like here. This is the pooled p hat. I'm going to store that to p. I'm going to store 1 minus that answer to q. Oh, no, I didn't store it to q yet. 1 minus p. Store that to q. There we go. So now when I do p and q, it gives me those proper numbers. It's just a lot easier to do it like that. So that if I were going to do the square root of pq over 1484 plus pq over 1013, it spits out the proper standard error that I'm looking for. 0.0123. They may ask you for this. And then if I'm going to calculate that z-score here, 0.13 minus 0.06 divided by that standard error, it would give me a z-score of approximately 5.68, which is going to be rounded, of course. Let me run the 2-prop z-test, because obviously most people are going to like this a lot better. If you're going to run the 2-prop z-test, it's going to make sure everything is typed in correctly. Less than, no, greater than. Yeah, greater than. Doing greater than. Calculate. There is that z-score that they were talking about. And there is the p-value. The p-value being 7.2 times 10 to the negative 9th power. That's way too low. We reject. We reject the null because p-value is approximately 0. There is evidence to suggest, you could even say strong evidence, there's evidence to suggest, and I go back to the original wording of the question, does this indicate that the proportion of U.S. adults who strongly agree with the given statement has dropped? There's evidence to suggest, go back to the context one more time. What are they talking about? People should take care of themselves. Okay. There's evidence to suggest the proportion of adults, U.S. adults, who think people should take care of themselves has dropped. Something along those lines. Crazy, crazy, crazy. I love problems like this. I really do. There's a lot more work that I did on the side that I'm not going to do with you, but I just wanted to kind of show you how that standard error was calculated, how that z-score was calculated, as a just in case. All right. There's one more problem I wanted to talk about, and it's number 6. I'll wrap up with number 6 today. And we'll see where this goes. And we'll see if we'll just shoot the breeze at the end, but I don't know if I can because of my son. Anyway, looking at number 6. A statistics professor has been teaching first and second semester statistics for 5 years. She wants to know if her grades in her first semester classes differ significantly from those in her second semester classes. She takes a random sample of final grades from her 2 most recent first and second semester classes and gets these data. Now, if you give me a moment, it may be helpful to type in this information. Now, some things that we do need to know while I'm typing this in. The classes are independent of each other. We can assume, or it's safe to assume, I should say, that the same students are not taking the same class twice. Now, randomness is also, I guess, well, I mean, she states it in the problem. Yeah, you could say it, yeah. Because of randomness, each student's grade is independent of each other. Let me just do a 1 var stat of L1. Make sure I got the right numbers in there. Yes, I do. Let me do a 1 var stat of L2. Make sure I got the right numbers in there. Yes, I do. Good for me. So here's some of the information that we have. We have an X bar. Let me bring this back. There we go. X bar of the first sample at 88.35 with a sample standard deviation of 5.314. Sample size is 20. X bar 2 is 85.35. Sample standard deviation 2 is 4.368 with a sample size of 20. We don't have a sample standard deviation. I'm sorry, a population standard deviation. We don't have a population standard deviation. We have quantitative data. This is a t-test. Now, is it a two-sample t-test or is it a matched pairs t-test? Well, it comes down to whether or not these two samples are independent of each other, and they are. Because of the context of the problem, we can assume that each sample is independent of the other. So, this is a two-sample t-test. Now, what's really interesting about this is that if you were going to do this thing by hand, and you would have to do a TCDF, you would need degrees of freedom. But unfortunately, you're not going to have to calculate degrees of freedom by hand. I'm going to run through this as if I were doing this on the actual AP test. So this is me on the AP test. I'm not going to do everything by hand. I'm going to have the calculator do most of it. Let me run through it. Null hypothesis. The question that they're asking, is there convincing evidence that the first semester grades and second semester grades differ significantly? Yes, Joe, it is. That's okay. People are tired. Since we're dealing with quantitative data, the null hypothesis is that there is no difference between the two. The alternate hypothesis is that, well, do they differ? There is a difference between the two. Random samples stated. Independence of 2 semesters assumed. Independence of student grades assumed. Because you're doing 2 sample, you have to look at both. 20 and 20, less than 10% of stat student population. You would also have to talk about nearly normal. Nearly normal, you're going to have to look at the histograms. Again, I draw a picture for the sake of time. I just want to show you what they look like. Here's the first sample. And here's the second sample. Both look nearly normal to me. Because of that, we're going to be running that 2-sample t-test. Now, you could do data with the lists that are in there, but let me just see what it looks like typed in. I'll do it like, yeah, I'll do it like that. I'm going to go back to data. I already wrote down the information up here, so we're good. And we're doing not equal to. Now, there is a question for pooled. Don't do it. Leave it on no. Trust me. Statisticians have debated whether or not you need to pool or unpool this junk. Just leave it unpooled for t-testing. Trust me. There's a long conversation about that. Calculate. Your t-score is 1.95. Your p-value is 0.0588. As a result, p-value is greater than 0.05. We fail to reject the null. There isn't enough evidence to show a significant difference in semester grades. And that would be sufficient. That would absolutely be sufficient. Oh, my word. I hope you all have been doing well. I will be assigning an assessment soon. I don't know when exactly, but you better believe it will be before the end of this week. Make sure, I know there are a lot of people that have just been kind of like coasting by, but that AP test is very important to me, and I have no idea how difficult this thing is going to be. I don't know. It's going to be a good time. Anywho, I think I hear my wife making a cake in the other room, and I am going to go join her. You guys stay well. Make sure you subscribe, and I'll see you all later.